So hypothesis testing on variance of a normal population, and we said we have different basically alternative hypotheses, and we can either use the rejection region method or using confidence interval or p-values. And this is basically the equations for calculating p-values, and this chi-square n minus 1 is the CDF function, which you need to integrate from chi-square from 0 to that number. We had one example, and for this example, we wanted to test this set of hypotheses. One is sigma squared is less than equal to 0.01, or sigma squared greater than 0.01. Okay? We actually use the rejection method, and the conclusion was what? We cannot reject H naught because the chi-square 0 that we calculated, which was this guy, it wasn't greater than chi-square of alpha over 2 and n minus 1 degrees of freedom, or 1 minus alpha over 2. So basically this guy. Okay? Because of that, we didn't reject H naught. So what I want to do, I want to use p-value and show you how to use this equation. Okay? So let's say we have the same example, but we want to use p-value method to see if hypothesis test should be rejected, null hypothesis test should be rejected or not. And let me change to two-sided. So let's say this is another example. Because one-sided is more straightforward. You can see it's easier. Two-sided is a little bit more difficult. So let's say we have same data set, but we want to test these hypotheses. Okay? And we want to use p-value methods. So first of all, we need to calculate the CDF of your test statistic. So your test statistics is n minus 1 s squared sigma squared divided by sigma squared. In this case is 29.09. Okay? Because you have s squared equal to 0.0153. Your n is 20, and your sigma 0 squared is 0.01. Okay? So what should I do? I need to find chi-square of this number, the CDF of this number, with 19 degrees of freedom. And if I do that, this number is 0.935, which is greater than 0.5. Therefore, so this guy here is greater than 0.5. I need to use this equation. 1 minus CDF of 29.09. Okay? So the question is how you can find this CDF. This CDF, you cannot find it in the table. But what you can do, because the table has only so many value of alpha. Okay? But what you can do, you can use R or MATLAB. Both of them have CDF for chi-square. So 2 times 1 minus chi-square of 19. And this number, again, is 0.935. At the end of the day, this is 0.13. So your p-value is 0.13, which is greater than alpha, which is 0.05. Therefore, do not reject H null. Okay? Does it make sense? So that's how you use p-value. How you use actually these equations to calculate p-value. Is it clear? Any questions? Nope? Okay. So, last topic for hypothesis testing for one population is for the Bernoulli distribution or binomial distribution. When you have a Bernoulli population with parameter p, and you want to test whether this p is equal to p0 or maybe not. Okay? And as you know, for large n, under H null, this follows a normal distribution, a standard normal distribution. Therefore, we can use the set of equations that we used before for basically hypothesis testing on the mean of a normal distribution. We can use the same critical regions. Okay? The absolute value of this z0 is greater than z alpha over 2. Reject it. For the one-sided also is this. And your z0 is p hat. What is p hat? You get a sample, and your sample from is x1 to xn. These are 0 and 1s. And then your p hat is the average of these numbers. Okay? So you have your p hat, your p0 is given, your n is known, so you can find z0. That's it. Very simple. Any questions? Again, n should be very large here because of central limit theorem. Using confidence interval. So what do? You calculate your confidence interval, two-sided, or here, one-sided, and then if p0 belongs to this confidence interval, you do not reject, otherwise you reject it. You've seen this confidence interval before, am I right? For one-sided. There is one difference, one thing unusual here. Anybody can tell me what is it? So, no, actually what I'm saying is the equations that you have here for confidence interval is a little bit different from what you had before or what you've seen before. No, that one is also alpha over by 2. Nobody can remember.
You don't normally use the p naught.
Yes, what we use is what?
Just p hat.
Exactly. So the confidence intervals that we used before, if you remember, was this guy. Okay? So we estimated mean and variance. So this is, we estimated the variance using the estimator of p hat. Okay? However, in this case, we are saying under H null, p is p0. So under H null, your estimator for variance would be p0 times 1 minus p0 divided by n. Okay? That's the estimator for variance. So use that one instead of p hat. For confidence interval, you don't have any p0, so you are not basically you don't have any hypothesis. Okay? So p naught is not there. That's why we have to estimate it using p hat. But in hypothesis testing, we have p naught. And we are saying under p naught, this is the variance of basically your test statistic, so use that variance. Okay? Any questions? Is it clear? Okay. So actually this is what I said. You can see for one-sided, I'm sorry, for the confidence interval, we are using P hat for both of them. However, here we are using P0, P naught. So one example is for the semiconductor manufacturing process. I'll give you a couple of minutes. Try to find the right hypothesis and then test that hypothesis. So the key point for finding whether it should be one-sided or two-sided, or if it is one-sided, which direction is here. So fraction defective at the critical manufacturing step, not exceed 0.05. That's the basically key sentence. Okay. So basically what it says if your customer says if your process fraction nonconforming is less than 0.05, then your process is capable. And you want to show the customer that your process is capable. Therefore, you want to see if your process fraction nonconforming or percentage of defect in your process is less than 0.05, and your null hypothesis is equal. Okay? So we need to find P bar first. In this example, it says 200 sample. How many of them? Does it say anything? 4? Yeah, 4. So 4 divided by 200, it's your P hat, and then let me use my cheat sheet here. Your Z0 is P hat minus P0 divided by P0, 1 minus P0 divided by N. 4 divided by 100 is 0.025. This number should be compared with Z. So alpha is 0.05. This is one-sided, so Z alpha is 1.645. And if you calculate this number, you get minus 195. Because your P0 is, so it's basically this guy minus 0.05 divided by 0.05, 1 minus 0.05 divided by 200. Okay? So What is the critical region for this type of hypothesis testing? Because it's one-sided. If I go back, you can see Z0 is less than minus Z alpha. So your Z0 is this guy. Let me write it down here. Your Z0, which is negative 1.95, is less than minus Z alpha, which is negative 1.645. Therefore, reject H null. Therefore, the process is capable. Okay? That's simple. Any questions? Yeah. A bias estimator for P. It depends on what estimator you're using. Okay? But let's say you are if you are overestimating, then your confidence interval is going to be larger. You know, forget about the hypothesis testing. Okay, let's talk about just confidence intervals. So here, this set of equations, if you are overestimating, your confidence interval gets larger. If you are underestimating, your confidence interval gets smaller. So when you are saying bias, depends on the direction of biasness. Okay, is it like positive or negative, overestimation or underestimation? Any other questions? Good. Okay. So let's see how we can define type 2 error. It's a little bit tricky for P. I try to derive one of these, and then the rest you can just use the equations. Let me see which one. The one which is easier. Let's go with this guy. Let's say your H null is P equal to P0, and your H alternative is P greater than P0, P naught. Then what you want to do, you want to find beta. So what is the definition of beta? Do not reject H naught given H naught is not true. That's the definition of beta. You agree? So we do not reject H naught is not true. So let's use mathematical formulation. So do not reject H null, which means in this case, Z0 is less than Z alpha. Because rejection region is Z0 greater than Z alpha. So do not reject is less than. So H null is not true. P is not P0. So P is something we call P1. I think in these slides I called it P. But P, you can replace P with P1. So that's what I mean. So we want to calculate this beta. So for that, actually, I just dropped the probability, sorry. So probability of this guy. So probability of, instead of Z0, I use P bar minus P0 divided by the standard error. This should be less than Z alpha, given P is P1. Any questions so far? Is it clear? So what I want to do, I want to just keep this one here, and the rest, because the rest are unknown, are known. Okay? And I want to calculate this probability, and I know that this is the only random variable that I have. Okay? So I want to isolate this guy here in the left side and move everything else to the right side, which is probability of, if I do that, probability of P less than P0 plus Z alpha times P0, 1 minus P0 divided by N. Okay? Any questions so far? Is it clear? Now, you tell me, what is distribution of P hat? Because I need to know this distribution to calculate this probability. Okay? Oops, sorry, I dropped the condition part. I need to add that condition part as well. P is equal to P1. Okay? So what is distribution of this P hat? Asymptotically is normal. What is mean? P0. Okay? No, that's not right, because we are saying P is equal to P1. Okay? This is under H alternative, not under H null. So with this mean and this variance. Okay? Does it make sense? Because P is equal to P1. So what I need to do, I need to standardize this quantity here by subtracting mean and dividing by standard deviation. So I continue here. My beta would be probability of P hat minus P1 divided by a standard deviation less than P0 plus Z alpha P0 1 minus P0 and minus P1 divided by P1 1 minus P1 n. So what is this guy? Standard, normal. Okay? And as you can see, I dropped the given condition. You see that? I dropped this given condition. Why? Because I already used this information here. Okay? I'm using P1 to standardize it. Okay? So Z less than a number. This is going to be phi of this guy here. Let's call it A. So your beta is phi of A, as you can see on your slides. Okay? So I said P and P1 in this slide are the same. Both of them are the same. Any questions? So as you can see, beta is a little bit more complicated than the case that you had for mean. The reason is what? The variance. So for normal distribution, mu and variance, mu and sigma squared are two separate entities. But for Bernoulli distribution, both of them depend on your P. Therefore, when your P changes, both of them changing, and you cannot simplify it anymore. Okay? So for normal distribution, that was variance, and that was also variance, the same quantity, you simplify. But here you cannot simplify. Okay. Any questions? Nope. How about n? These are the equations for n. I don't derive it because I know that you know how to derive it. You can just use this equation, solve it, this equation actually, solve it for n, and you get exactly what you have over there. Okay? So P, again, is P1, P0. P1 and P0 is given. Alpha and beta are given. And then n, you can calculate n. So it's basically, again, if you use this n, your power, your detection power, or the power of your hypothesis test for detecting this change from P0 to P is 1 minus beta under alpha type 1 error or significance level. Okay? Here is one example. Same example, I think, erased it. Anyways, so for this hypothesis testing, where P is equal to 0.05 or P less than 0.05, so you want to calculate beta. So what is the beta error if your actual P or P1 is 0.03? It's not 0.05, it's 0.03. So what is your actual P? Is 0.67, based on the equation that we already derived. Okay? So what does it mean? So if your actual P is 0.03, and you use this hypothesis testing, with the probability of 0.67, you cannot reject H null. So you cannot identify this change or detect this change. Okay? Which is very high because your power is 33%. So the question is, what if you want to increase your power? The next part says, what if you want to increase your power to 90%? So from 33% to 90%. Then you can use this equation to find the n which is required. In this case is 832. So the original n was 200. So you need 4 times bigger sample size, more than that actually, to have a good and reasonable power. Any questions? Is it clear? Good? Okay. So OC curve for t-test. For t-test, we don't know how to calculate alpha and beta. But if you want to calculate alpha and beta based on different n, you can use OC curve. These are in practice, we can use them. For example, D again is a scaled change in the mean. So your x-axis is D, which is mu1 minus mu0 divided by sigma. Okay? And you have different curves here. When there is no change, this is what? You remember? 1 minus alpha. And when D is greater than 0, these are curves representing beta. Okay? And as you can see, when n increases, your beta decreases. So for example, for this magnitude of shift or change, your beta for n equal to 3 is around 90%, but for n equal to 7, it's down to, let's say, 15%. And this is OC curve for t-test for 2 different values of alpha, 0.05 and 0.01. And as you can see, this is 95% because your alpha is 0.05. This is 99% because your alpha is 0.01. Okay? For chi-square, as you can see, this is symmetric. That's why I don't have negative numbers here. So it doesn't matter what is the direction of change. Is it positive or negative? You get the same beta. But for this guy, you can see, basically for chi-square test, the direction does matter. Okay? So your OC curve for the right direction and left direction is different. By the way, for chi-square test, this is the hypothesis that we are using, if you remember. And sigma squared is not sigma squared 0. So your x-axis here is not the difference like D. It's the ratio. So let's say sigma 1 divided by sigma 0. So that's the ratio. This is lambda or x-axis. Okay? If lambda is equal to 1, means what? H null. So For lambda equal to 1, this value is 1 minus alpha. For the other values of lambda, this is beta. Exactly. Any questions? What is it? You good? Okay. Yep. Let me just double check. One-sided OC. No, it changed. It's not that simple. Because your alpha changing over there. I mean, not your alpha, but your critical region is changing. I think this is for two-sided. Yeah, you can see. There are, but I think in your book, you have one-sided as well. Yeah, I don't have it here. So you have for one-sided also in your book. Any other questions? You're good? Question? Good. Okay. So you learned how to do hypothesis testing for mu, sigma squared, and p, which is basically normal distribution and Bernoulli distribution. How about other distributions? Okay, what if you have, let's say, Weibull distribution? What if you have Poisson distribution, exponential distribution? How you can construct a confidence interval? So again, you remember when I told you if you have MLE, it has some nice properties. What is the most important property of MLE? Norm, exactly. Approximately follows a normal distribution if n is large. So asymptotic distribution of an MLE estimator is normal. Therefore, you can use this basically property to develop other hypothesis testing for other distributions. Okay? Here is one example. This is an example for Poisson distribution. Okay? Let's say we have the number of open circuits on a semiconductor wafer follow a Poisson distribution. We have a sample of 500 wafers. As I said, sample size should be large because we are talking about asymptotic, basically, behavior of MLE. And out of these 500, I find 1038 open circuits. Okay? So as you can see, the 1038 is greater than 500, which means on each wafer you have more than 2 defects, or more than 1 defect. Okay, on average. Test the hypothesis that the mean number of open circuit per wafer, which is basically the definition of lambda, exceeds 2. So what we want to do, we want to test whether lambda is equal to 2 or greater than 2. So the first step always is to find the estimator for the parameter that you are performing hypothesis on. Okay, in this case, lambda. What is the MLE estimator for lambda for Poisson distribution? Is X bar. Okay? So if you derive that, take the derivative, you can see that lambda hat is X bar. Now, the second part is find the mean and variance, because if you remember, if I want to give you a general setting, forget about Poisson. Let me give you a general setting, and then I use Poisson as one example. So let's say X follows a distribution that has one parameter theta. Okay? Then I want to see whether theta is equal to theta 0 or it is not. So first step, find MLE for theta. Let's call it theta hat. Second step, find the expected value of your MLE mean and variance of MLE. In this case, is expected value of theta hat and the variance of theta hat. Okay? So we know that theta hat follows a normal distribution. Let me write it down here. Theta hat follows a normal distribution with this expected value and this variance. Okay? So I can use this property when n is large. Okay? And the third step, I can define Z0 as theta hat minus theta 0 divided by, or let's do this. So this is under H null. Okay? So I call this guy expected value under H null. I don't know, this is not a good representation, but I don't know how to show it. Let me see. A better way of showing this is expected value of theta hat under theta 0 and variance of theta hat under theta 0. So what do I mean by that? The expected value of theta is a function of theta hat. You replace theta with theta 0. Okay? You will see an example. And then fourth step is to compare it with your critical region because it's normal distribution. Now, for Poisson distribution with parameter lambda. So I want to see if lambda is equal to 2 or greater than 2. Okay? So what is the first step? Find MLE. Find MLE. So MLE for lambda is x bar. Second step, what is the expected value of x bar? It's the same as expected value of x, which is lambda in this case. What is variance of x bar? Is variance of x divided by n, which is lambda divided by n. Okay? The third step, find z0, which is x bar minus lambda 0. So as you can see, here is what I meant. So your expected value depends on lambda. Replace lambda with lambda 0. Okay? Instead of using lambda, I'm using lambda 0. Divided by lambda 0 divided by n. And this z0 in this example is divided by 500 minus 2. 2 divided by 500. This guy is 1.2. And the fourth step, you already have it over there. You compare z0, which is 1.2, with z of alpha, which is 1.645. This is less than that. We do not reject H null. Okay? So if you have Weibull distribution, if you have gamma distribution, if you have beta distribution, anything, you can use this method. Okay? Again, this means when you get the expected value, it depends on the parameter of the distribution. Just replace that parameter with theta 0. That's what I mean by this notation, which is very weird notation. Any questions? Okay. Just give me a second. I need to... So we are done almost with the hypothesis testing for one population. The next topic is how we can compare or perform a hypothesis testing for the mean and variance of or fraction non-conforming of two populations. T square. Okay. So for two populations, let me start with the simple case. When you have two normal populations, variance of both of them are known, but you want to see if the mean of these two populations are known, are equal or not, which could be inequality or greater than or less than. So you remember we had confidence interval for that. We know that x bar minus y bar, if I have two independent samples, this x bar minus y bar follows a normal distribution. Therefore, this guy is what? The standard normal again. Since it's a standard normal, let me see if I can make it bigger. Yeah. Since it is a standard normal, then I can use basically the equation that we had. I think oh boy. I don't have the slides for, I thought it's already there for one population. So that's for two populations. That's okay. I start writing it down. So what should we do? So we need to find z0, which is x bar minus y bar minus mu1 minus mu2. Okay, under H null, mu1 minus mu2 is what? Is what? Under H null is 0. So divided by standard deviation, which is this guy. And what should I do? I need to compare z0 with z alpha over 2 for this alternative, for this alternative, which is mu1 is greater than mu2, I use this guy. For mu1 less than mu2, I use this guy. So these are the critical regions, depending on what alternative you have. Okay? So x bar is the average of the first population, y bar is the average of the second population, and this guy is going to be 0. These are given, you can easily find basically the z0 and then compare it with the critical region. Okay? So another method is what? Confidence interval. So you find a confidence interval for two-sided in this case. Okay? And what? Remember, we use confidence interval. We say mu0 belongs to this confidence interval. We do not reject. How about this case? What can we say? If what? If 0 belongs to this confidence interval, then we do not reject H null. Otherwise, we reject H null. So, because mu1 minus mu2 under H null, this is 0. So, if 0 belongs to the confidence interval, Do not reject H null. Otherwise, we reject it. Okay? For two-sided, this is for two-sided, for one-sided, the same thing. Okay? So basically, if 0 or this case is negative infinity and u. Okay? Okay. I don't know. I thought I already posted these slides. I don't know why. I was under this impression. Anyways, we continue on Friday for two populations. So when we are done with two populations for hypothesis testing, then we have two or three more different topics. One is regression, and the other one is analysis of variance. When you have more than two populations, let's say you have 3 or 4 populations, how you want to do basically hypothesis testing for that. Any questions so far? So I try to, because your abstract is due in sometime in April, am I right? Yeah. Yeah. So what I'm trying to do is to teach you analysis of variance and regression, at least conceptually, so you know what to do for your project. Okay? So essentially what you need to do, find a problem, okay, and try to solve that problem using what you learned in this class. Hypothesis testing, descriptive statistics, everything that you learned so far. And that's why I'm saying you need to also see what ANOVA is about and what regression is about. Therefore, you can basically have a better problem definition. Okay? I'll see you on Friday.